Hello everyone. I hope everyone is staying healthy and happy. Let's get logistics out of the way before we dive into today's lecture. I hope everyone is working hard on P10 and the final project. P10 is due 2 days from today, which is Friday, May 1st. The final project is due a week from today, which is May 6th. All right. That said, let's talk about today's lecture. So, today's lecture is going to be the culmination of the series of lectures on the topic of plotting. This is going to be the fourth such lecture. I'm a little bit sad because this is going to be the last lecture that I will be recording, even though you have one more lecture, Mike is going to be recording that. All right, let's talk about reading for today's lecture. As with the previous plotting lectures, this plotting lecture also has a reading which was put together by Tyler. So let me quickly talk about the topics that we are going to cover as part of today's lecture. So we left off halfway through the example for the fire hydrants data set from the city of Madison. We are going to wrap that up first. And then I'm going to talk about how to set limits for access for various plots. And then I'm going to talk about what logarithmic scale is when it comes to plotting. Finally, I'll wrap up plotting topic by talking about how you can generate multiple plots within a single figure. If you spend some time going through this particular HTML version or the notebook version of this document, you'll find that this is a really interesting write-up. And if you scroll way down to the bottom, you'll see that Tyler has provided a lot of good insights on this really difficult question of which plot is the best plot when it comes to answering a specific question for a specific data set. Recall that during the first lecture on plotting, I mentioned that it's very easy for you to be able to write code for generating any plot. All of you have learned enough Python programming to be able to do that. But the difficult question when it comes to plotting is trying to find which is the best plot that you can possibly plot given a scenario for like a question answering a particular topic from a data set. All right, let's talk about today's lecture code. So today's lecture code is going to be split across two different files. I'm going to go ahead and continue demo lecture 39, which is going to wrap up the fire hydrants example. And then I'm going to move on to the new notebook file to talk about the new topics for today. I'll make sure to copy both have a copy of lecture 39 file updated in the lecture 39 folder and also in the lecture 40 folder. Alright, with last couple of classes, there are template files for you to download and pause the video and go through. So let me go to demo lecture 39 file. One thing I want to mention here is to answer these series of questions, you actually know a lot of information. So if you'd prefer to pause the video here and try to answer those on your own and then come back and verify your answers, I would recommend you to do that. Alright, let me do a quick recap of what the fire hydrant dataset is. Recall that the fire hydrant dataset has all the information about fire hydrants within the city of Madison. It has things like what is the color of fire hydrant and what is the style of fire hydrant and other associated details like latitude and longitude and so on. So where we left off this example during last lecture is that we created this bar plot in order to plot the hydrant count within each style of the hydrant that is available from the data set. So often a follow-up question to such a bar plot would be, how exactly can you describe other details of the highest bar over here, which is representing the pacer style of fire hydrant, right? So one such question could be, in what decade were pacers manufactured, for instance? Similarly, when you're talking about one particular style, you can always include the rest of the data as others, as we have seen with multiple examples when it comes to plotting. All right, let's try to get through these series of questions or notes. The first one is a note which says, take a peek at the style column data. Let's go ahead and do that. So DF is going to be the data frame. Let me actually go ahead and confirm that. Yeah, DF is the data frame. And I do know that, I do remember from the previous lecture that style column is given by the name style with a capital S. And let me go ahead and do a head. You can feel free to also check out the tail as well every time when you're going through something like that. So interesting thing is this style column could have NaN values. So we'll have to handle that shortly when it comes to a specific counting conversion step. All right. That question is done. Let me move on to the next one. The next one is asking which column gives year information. So recall that you can use df.columns to get all the list of columns. If you're guessing year underscore manufactured is possibly going to give you the year information, that is correct. So let's move on to the next question, which asks how to get the decade for pacers and other types of fire hydrants. So let's first actually get a combination of both the style and the year manufactured columns. So recall that if you want to extract two columns, you can just like mention a list of columns as the argument that you pass to the df lookup here. So the first column is going to be style and the next column is going to be year manufactured, and let me go ahead and do a head of this. As you can see, we are able to retrieve both the style and the year manufactured as well. All right, so let's move on to the next, so let's move on to answering the next aspect of this particular question. So we know how to retrieve the years for specific style entries, right? So the question here is asking how do we actually extract the decade from it? So let's first actually extract the years for pacer style and for the others. So the way that I'm going to do that is we just need to use the Boolean expression, right? df of b, where b could be a series, and in this case the series would be df of style being either pacers or the other case, right? So this is going to give the entire data frame, but what we need is just the year manufactured column for that particular matching Boolean expression. So let me actually go ahead and assign this to a variable called pacer underscore years, and let's take a peek at pacer years data frame just to make sure we are getting the correct values. There we go. Okay. The next thing that we want to do is the opposite of this, right? We want to go ahead and extract years for other style of pacers, other style of fire hydrants other than pacers. So let me go ahead and take a peek at the other years data frame, which seems to again be fine. All right, so let me actually leave a print statement of these two for your future reference. So I'm just going to say pacer years dot head and other years dot head. There we go. All right. The next thing, now that we have the individual years for each fire hydrant, which is of style pacer, and anything other than that as part of other years, let's talk about how we can actually get the decade for pacers and the other fire hydrants. So there is a neat trick that you can play when it comes to extracting decade from given a year, right? So you can very easily use integer division for that. So let me show you what I'm talking about. So let's take pacer underscore years as an example, and let's say that we try to divide use the regular division by 10. That's going to actually give you a floating point result, right? Recall that integer division gets you the same the same division operation, but rounded to the closest integer. So now that you have extracted the first three digits, it's very easy to just multiply the same value by 10 to get the decade value here, right? So we started with 1996, and now we have 1990 after this operation. All right, so let me reassign this to a variable called pacer underscore decades, because years are now decades after this conversion. So, and we want to be able to do the same conversion with the other style of um, fire hydrants as well. There we go. All right. So we now have answered this question, how to get decade for pacers and others. So let's go ahead and answer the next question, which is how to count the decades for pacers and others. Recall that you can use the value underscore counts function on a data frame. So let me go ahead and change the above cells code, and let's make pacer decades have the count of decades instead of just each of those decade entries. So I can just invoke the value underscore counts function on this data frame before we go ahead and extract the specific decades from that particular data frame. Let me actually do a display of pacer decades and other decades series here, so that you can take a look at what's going on. All right. So one interesting observation that you can see from the data here is pacers are a little bit outdated, whereas other fire hydrant models seem to have replaced some of the pacers. But somehow pacers still seems to be the most popular fire hydrant in Madison. All right, now that we have answered this question, let's move on to the next one, which is asking how to convert the decades back into integers, because we have a floating point value here. Why did we get a floating point value here? That's because we did an integer division, which returns a floating point value even though the result is rounded off to the closest integer. All right. Recall that you can use AS type function call on a data frame. So I'm going to actually go ahead and do that before we extract the value counts. I'm going to actually show you this example first for pacer underscore decades. That's because we will run into a problem when we do this. Recall that I was talking about the data set having NaN values, and that might cause us problem in the future step. So there is a reason that you're getting an error here. That's because you cannot actually convert a NA value into an integer. So this will lead to error because, let me put it this way, it doesn't work because of NaN values. Alright, so how do we actually fix this? So there is an easy solution to this problem. Pandas allows you to get rid of all the NA values with a very quick function call, which is, let me actually go ahead and rerun this cell so that we don't have that whole error message there. Pandas allows you to drop NA values very easily with a function call, which is called as drop NA. So I'm going to go ahead and drop the NA values, and then I'm going to convert to integer type over here before I do the value counts. So let me go ahead and I forgot the drop NA for the next one. Let me go ahead and show you the result after this. There we go. You can compare and contrast with the previous result. Nothing should have changed other than the decimal point value which you had for decades. Alright, let's move on to answering the next question, which is asking how to put both pacers and other decade count series together. So recall that whenever you have two different series that you're trying to plot within the same graph, you can very easily combine them by creating a dictionary where like each of those series is going to be a value, and then you have the column name as the key to those series, right? So let me create a data frame called plot df. So I need to be able to create a data frame from scratch, so I'm just going to call the constructor, and we are going to be using a dictionary to create the data frame, right? So in this particular case we have two series, so I'm going to use the first series column name as pacer, and the next one as other. And what do we need here is the actual series itself. So we have that from pacer decades and from other decades, right? So let me replace the next variable. There we go. What else is missing? Let me go ahead and run that, and then we'll see. Things seems to be fine. Alright, so the only thing that I'm going to do with this particular data frame, let's actually peek at the data frame, is that I'm going to plot the data frame and create a bar plot with it. Before that, I just want to quickly talk about how Python actually merges the indices for these two series. So these two series actually has indices as those particular years, right? So the way that this merge works is if one of those data frames, not data frames, series doesn't contain an entry for a particular year, Python will actually replace that value with a NA value. That's what you're observing here, because pacers don't have data from 1900 and many other row entries, because the other decades had many more decades than the pacers. Alright, if you were to merge two different lists to create a data frame though, then Python would actually renumber all the row indices starting from 0. Alright, let's move on to the last note here, which says we want to be able to create a bar plot for visualization, right? So it's very easy for us to create a bar plot with plot underscore df. We just need to say plot dot bar, and let me capture the axis subplot variable because I want to be able to set the x-axis and the y-axis. So let me go ahead and display that first. So x-axis here is years, and decades actually, sorry, not years, and y-axis here is going to be hydrant counts, right? And we already have the label, so the legend label, so that's good. All right, that's a decent looking plot. What you can think of doing in order to improve this particular plot is that sometimes when you have multiple bar plots like this, sometimes it might make sense to actually stack them up. So the reason why they're good when stacked up is, in this particular case, it totally is understandable because the total count all tallies up to the Pacer models from that particular decade. So you either have a Pacer style fire hydrant or other style fire hydrant. Both of those can actually be put together to form one single bar. And that's going to be one change that we are going to do. Another thing that you'll notice is this particular data has very less information from like very old decades like 1900s. You probably will be interested in looking at recent data, let's say from 1950, where more information is available. You can very easily make the plot just consider the x-axis values from 1950 by taking a sub data frame, right? So you can just say plot instead of plot df plot dot bar, you can say plot df of a boolean expression, and in this case the boolean expression would be plot df dot index greater than or equal to 1950, right? So you want your indices to be considered from 1950. Alright, so let's go ahead and see what that particular plot looks like much better. Going back to fixing the stacking of the plot, so that's actually a parameter for the bar function. You can just say stacked equal to true. That's going to actually stack up the plots on top of each other. There you go. So that's an example of creating stacked bar plots. That's it for the fire hydrant data set from the city of Madison. Feel free to explore more options in this data set. It's an interesting data set. All right, moving on to other lecture topics for today's lecture. So the first topic is going to be about how to set x limit and y limit on any given plot. So recall that we were talking about the iris dataset couple of lectures back when we did scatter plot. So this is the dataset which is commonly used in machine learning. It talks about various features of iris flowers, and we had three different classes which we sort of created the scatter plot for, right? So today what we are going to do is we are going to focus on one particular class here, which is called as the Iris virginica class. No specific reason. You can pick any of those classes, but I'm just like picking the Iris virginica one. So what are we going to consider is we want to plot the data just for Iris virginica. You already know an answer to this particular question. How do you extract the data just for Iris virginica? You can just apply a Boolean expression to extract the sub data frame. Let me call that as df underscore sub, and what do we need to get as into the sub data frame is only the class entries which are for Iris virginica, right? So let me actually copy paste. Oh, sorry. Let me actually copy paste this string so that I don't get it wrong. Somehow I'm not able to get that correctly. Let me actually copy paste it from up here. Sorry about that. Alright, so let me do a df dot sub of head just to confirm. Yeah, something is missing. Okay, I'm missing the double quotation. Something is still missing. Huh? Interesting, I'm running into too many problems. Okay. So the variable name is small c, I think. The column name is small c, I think. There we go. All right. So I do know that there are actually 50 such entries from the original data set. So if you do know some information like that, you can easily add an assert saying, okay, length of df underscore sub should be exactly 50, and you can yeah, let me actually leave this for your reference. So I'm going to leave a head display of that particular data frame. All right, we have extracted the data just for iris virginica. Let's try to answer or look at the next note here, which talks about x limit and y limit. So before that, I want to show you the scatter plot for just the data from the iris virginica class. So recall that scatter plot requires two arguments, which is the x and the y parameters. So x is what we have done in the past is x has been petal width and y has been petal length. I'll just maintain the same, and let's take a look at the plot over here. All right, there we have the plot for just the iris virginica class. So one thing which is very difficult to read from this plot is you can't really say how the petal width varies with respect to the petal length, right? Because the x-axis and the y-axis have entirely different range here. You can't really talk about, okay, what is the relationship between those two factors for that flower. So that's what we are going to learn to control today. So we are going to learn about x-lim and y-lim parameters, which are going to enable you to set the limit for the x-axis and y-axis. So the default value for those, let me say, come directly from the data, which is from the data frame. Let's actually go ahead and explicitly set x limit here to, let's say, 7, for example. And then if you take a look, oh, I think I said the, I need to set a lower value. Sorry about that. Yeah, I'm trying to set the lower value here and not the upper value. I got that mixed up. So if I set x limit to 0, the graph is slightly more readable than before. And similarly, if I set y limit to 0, that is going to make the graph a little bit more readable because the axis, both the x-axis and y-axis now start at position 0. So what would be even better is that if you can provide a range of x limits and y limits, right? That's very easy to do actually, because x limit actually takes x limit and y limit takes a tuple of values, the values being lower bound and upper bound. There we go. So let me actually show you as an example here the ranges 0 to 6 for each of those limits. So typing that got rid of one of those parentheses. All right. If you're following this data closely, you'll notice that there is actually one major flaw with setting x limit and y limit. What I did right now is I actually effectively cut off a few data points. Somehow Python is allowing me to do that. I really wish that Python wouldn't actually allow me to do that, because I'm accidentally erasing some of my data. But unfortunately, we have to write our own assert statements to control this. So this line is becoming much longer, so I'm going to go ahead and cut it short. And I'm also going to make the figure size square over here. Recall that fig size parameter takes a tuple value for width and height of the figure. I'm missing a comma. There we go. Much better than before now that it's square. So let me show you how you can actually go ahead and write an assert statement to verify that you're not cutting off specific data points from your data set. So there are two different aspects here, right? One is the x limit and y limit of the plot itself, and other is what is the maximum value from the data frame. So let's look at the maximum value from the data frame for petal length. So you can just do df underscore sub of petal length and call the max function. luckily Pandas supports that. All right, so 6.9 is clearly greater than 6, right? So let me show you the other aspect of comparison here for the assert statement, which is like you can get y limit by saying get underscore y limit. And let me show you the value here. Oh, it looks like I didn't actually capture the access plot object into the variable called ax. Hopefully this will work now. There we go. So the get y limit will give you a tuple of values. The lower bound is the first one and the upper bound is the second one, similar to what you follow while setting the x limit and y limit. So how can you actually write an assert to make sure that Python doesn't actually allow such a plot? That's quite easy, right? So you have both the sides of comparison aspect over here. One is the maximum value of the data frame and the other one is the y limit. So you just need to compare them both and include that as part of your assert statement. So what we want to do is we want to be able to ensure that the max is within the bounds of the y limit over here. So one thing to notice is your y limit is actually returning a tuple of values. Since we're trying to create a comparison for the max bound here, we need the first value, which is 6 over here. So hopefully that should give us an error now. There you go. The assert is getting hit and you are getting an assertion error instead of just like going ahead with the plot without any errors. All right, so let me actually complete this for all four of the checks which are needed here for the x-axis and y-axis limits. So one thing you'll notice that instead of always fetching the max value from the data frame, you could very easily replace this part over here without having to remember what column name that you're looking for. You can just say ax dot get underscore x label. That's going to get you the x label. Wait, I need to get the y label, not the x label. Y label for this particular case. All right, for the other two options, we just need to set the x label for the x max value. What do you do for the min value though? Your sign should change here for the min value, right? So your min value should be greater than or equal to, and this should be your lower bound for the min value. Similarly, the fourth one should be min, and that should be for x-axis instead of y-axis. Alright, so if I go ahead and do that, you're going to get a lot of assertions. So let me actually fix this with the correct x-axis and y-axis limits. I'm going to change the range to be 0 and 7. Hopefully, looks like we are still getting an assertion error, which means that one of these comparisons is actually incorrect. Let me actually quickly see if I'm able to spot it, or else I'll correct it later for you. So which one of those is giving me an assertion? It's giving me an assertion for line 8. Oh, let's see. I did get the x-axis label correctly, and let me take a look at what is the min of the x-axis label and why is that giving me an assert. So that's 1.4. I forgot to change the sign for the other minimum. That's the reason. There we go. Hopefully, yeah. We fix that issue. Alright, so that's how you can set x limit and y limit and make your plot much more readable as per your custom requirement. Alright, let me move on to talking about logarithmic scale. So in order to introduce logarithmic scale, I'm going to import the math modules. I'm just going to scroll way up here and add a cell after all these things and include the math import. There we go. Alright, so scrolling back down, the function that we are going to talk about today is math dot log10. You can also use a generic log function called math.log, which takes two parameters y and base. I'm not actually going to talk about that, but I leave that as a note here. So what are we going to do is I'm going to explain to you what exactly the math.log function does by showing you an log10 function, not log function, sorry about that. Log10 function does. So math.log10 of 1000 is 3. So to give you a simple reverse explanation, math.log10 is sort of going to find a value x such that 10 to the power x is given by the value y. And what is y? That is the value that is going to go as part of your function parameter call. So math.log10 of y is going to find an x such that 10 to the power x is equal to y. So 10 to the power 3 is 1000. So that's why your answer for math.log10 is 1000. Alright, so understanding log is often tricky even for STEM researchers. So I'm going to give you a very simple explanation. We are going to write a pseudo log function which is not quite the equivalent of a log, but it's close enough. I'm just going to call that function as log e. So as an equivalent to the log10 function, not an exact equivalent, an approximate equivalent or a pseudo equivalent, you can think of this very simple approach where you need to ensure that type of y is always an integer. So I'm going to go ahead and add that as an assert. So the next rule for this particular conversion is first rule is that y should be an integer. The next rule is that y should be positive, so y should be greater than or equal to 1. It should be a positive integer actually put together. You can write a single assert statement if that's more preferable. Alright, so the way that you can approximate log base 10 is by first converting y to a string value, and then you can go ahead and take a length of that particular string, and that value is going to be close enough. Let's actually take a look at a couple of examples here to see if that is actually true. So I'm going to go ahead and try log a of 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's see what that generates. That generates a value of 9, right? Clearly you have 9 digits. So let's see what math.log10 generates for that. As you can see, it's like somewhere close to 8.09, which is a decent approximation. Let's try out a couple of more one more example here. So let me say 989898 another 98 for example, and let's see what log e returns. Log e returns an 8, and let's check what math.log10 returns. Alright, so that returns 7.9, which is quite close to 8, right? Alright, so let's actually talk about what is the bound of error with respect to whatever log e returns as opposed to what log10 returns. To be able to find a bound of errors, we need to try out a few samples, right? Let's say that we want to try out all the values from 1 to 1 million. I'm going to say in a for loop for I in range 1 million, 3 zeros, 1, 2, 3, 3 zeros, that's a million. What we want to do is we want to be able to compute the error between log e calculation and log e function calculation in the math.log10, right? So recall that you cannot take a log for 0, so we are going to get started with 1 instead. So I'm going to say y equal to I plus 1, and what we want is this error bound something minus something over here, right? So what is this second something, or like one of these somethings going to be is like we want log e of y, and in the other one we want mat.log10 of y. There is no way for us to say which one will actually be bigger, right? So I'm going to go ahead and take absolute of this difference, and let me actually track this error for all of these entries. So I'm going to append these errors into a list called errors, and let's take a look at what is the maximum value of the error bound over here. All right. The maximum error difference between log e and math dot log 10 is 1, which is not bad, right? That's a close enough approximation. So you might be wondering why does all of these things matter? So let's talk about comparing two numbers over here, and I'm going to type random digits. So let's say this is one number and this is the next number. So do you really care about the digits when it comes to both of these comparisons? Eventually, as the number gets bigger and bigger, the answer is no, right? You don't really care about what exactly those individual digits are. Rather, you want to know how many digits are there in the number. When I type this out, it's very evident that the first number is so much bigger when it comes to second number, right? So that's exactly what logarithmic scale is enabling you to do. So it's moving the focus. So log base, I should not be using capital. So log base 10 is sort of moving the focus into the 10 digits, which are 0 to 9 digits, right? And similarly, log base 2 is going to count how many bits we need to provide a similar context. All right. So now that I've given some introduction to logarithmic scale, let's take a look at plotting with respect to logarithmic scale. And for that, I'm just going to use a series as an example where I have like numbers, say a list of numbers, say from 1, 10, 100, and let's say I'm going to do that until a million. Hopefully, I'm doing that correctly. All right. So let's say I want to go ahead and create a line series plot with this particular series. So as you'll see, such a plot is actually very misleading because it makes you think like up until your fourth 0, 1, 2, 3, 4 fourth index here, which is 10,000. No other value before that has any significance at all, right? Of course, that's true because 10 is so much smaller when compared to a million, right? So how can you actually draw a plot which doesn't diminish the value of smaller numbers whenever your data has such a huge number? And that's why you have the logarithmic scale, right, when it comes to plotting. So how do we actually mention that you want a logarithmic scale? So you have a parameter called log y whenever you're plotting a function. Whenever you're calling the plot function, you just need to set the log y parameter to true. So now you'll observe that you're able to clearly say, okay, the first entry is 10 power 1 and second is 10 power 2 and so on. And of course, you're able to see a linear line here. That's because the scale on the y-axis is actually logarithmic. So the scale always matters a lot. So you shouldn't think that this is actually linear scale without considering that the y-axis is logarithmic. All right. Hopefully that example made sense. So one highlight that I want to mention is this log y parameter has nothing to do with the log e function that custom function that we wrote. So I just want to make that absolutely clear. All right. So the last thing that I'm going to talk about in this lecture is how to actually create multiple axis subplots in the same plot. So recall that a couple of lectures ago I showed you how to import pyplot from matplotlib. You need to say from matplotlib import pyplot as plt. I'm going to go ahead and move this up to the import statements. All right. So recall that plt.subplots function call will enable you to get a tuple of items. So the first one is the figure object for the plot, and the second one is axis subplot for the plot, and of course we are creating an empty plot like that, right? So I'm going to talk about how you can create multiple axis subplots with this subplots function call. You can just mention the parameters n calls or n rows to this particular function call, which is going to split the axis, your figure into multiple axis subplots. So for instance, n calls equal to 2 is generating kind of a list of two subplots, right? Why am I saying kind of a list? Because it's actually not exactly a list. It's another data structure called NDRA. I'm not going to go into details of that, but I'm just going to mention the name. All right, so you can, this splits the figure into two vertical plots. You can do a horizontal one by saying n dot rows equal to 2, or you could have a quadrant of plots by adding both of those parameters here. All right, so oh, I made that to be too many plots. There you go. How can you actually mention which plot goes into which axis subplot? Let's actually take a look at a very simple example for that. Let's say that I'm trying to create two vertical plots over here, and I want to plot two different series. So let me have the first series as 1, 2, 3, 3, and 4. I essentially added another 3 so that it doesn't look like a flat line, linear of linear growth. So I'm going to go ahead and plot the line. So recall that this particular, where is the n calls to function call? There you go. So the return value is like you have two different sets of values in this tuple. The first one is the figure, and the next one is axis subplot, and within the axis subplot you have this ND array, which is going to have two different variables, right? So I'm going to go ahead and extract both of those from here. And how can I say where this particular plot should go? So if I don't say anything, let's see what happens. So it randomly picks one of those two, or I think it picks the right one. I don't remember which out of those two. But if you want to be able to control which out of those two axis subplot that you want your plot to go into, so your axis here, let me actually remove this and let's display just what is there in axis. So axis is an ND array, right? So if you want to extract the first entry, it works similar to an array. So you can say axis of 0. So that's going to make the plot go into the first, axis subplot. Or if you say 1, that's going to make it go into the second subplot. Alright, so let's say I have a different series, and let me make the values a little bit bigger. 5, 7, 7, and 8 and 9, for instance. So, and I want to plot this one on the next axis subplot area. One thing you'll notice is it's the graphs right now are misleading. That's because the y-axis range of values is totally different, right? So if you want to make your plot very much readable whenever you have like subplots like this, you need to make sure that you have your y-axis shared. So the way that you're going to be able to do that is use a parameter called share y whenever you're making the subplot function call, and that's going to make your graph much more readable because both the plots share the same y-axis. All right, I'm going to go back to the reading here for a quick minute. So if this class were in person, we would have gotten to, vote about these few set of examples which Tyler has given way down here to compare which out of these plots would be better suitable, because both the plots are plotting the same information. I'd recommend you to go through each of these and think about which particular plot you think makes more sense, and that's going to give you a clear sense of why it is really important to choose a particular type of plot whenever it comes to answering a question for a given data set. All right, that said, that's it for today's lecture. That's it for lectures from my end, actually, for 220 course for this semester. That said, I'm going to be recording a video message for all of you, which Mike said he'll put together as part of the last lecture for 220. I wish each of you the best of luck for a bright future.